We're going to be talking about sections 13.3 and 13.4, which are going to talk about arc length, speed, and curvature. We're going to start off with arc length.
So, arc length, measuring the distance we have on a path. So on a path, you can think about walking along your path and how far that would take you to get from here to here. We have some ways of computing this using calculus. We're going to be doing some ways of, like Riemann sums for old school integrals. We're going to take small chunks and add them up over time to, well, use calculus to do all of our work for us.
Yeah. So let's say that this path is given by some vector valued function r of t. And I want to know, as I travel from r of t naught to r of t1, how far have I traveled? We're going to do this by approximating it with a straight line segment. In vector valued notation, I can represent this line segment as the difference r of t1 minus r of t naught. As I travel from t naught to t1, I'm undergoing a change in time. Typically, we represent that change in time as a delta t. So an equivalent way to represent this difference is to represent it as r of t naught plus delta t. So that's our t naught plus a small change in time minus our original r of t naught. This piece right here looks familiar to us, that we've seen this piece before when we were calculating derivatives. In fact, we can approximate our derivative, r of t is approximately equal to the difference r of t plus change in t minus r of t, all divided by this delta t. Of course, this would be exactly equal if, as we take the limit, as our delta t's go to 0. And so we're going to look at this piece is actually exactly equal to r of t times our delta t, which is r of t plus delta t minus r of t. So why did I do all this stuff? What is all of this stuff saying to us? So we know that this vector, represented by r of t1 minus r of t naught, if I want to know how long this vector is, I'm going to look at the magnitude of this vector, which, going all the way down here, would be looking at the magnitude of each of these pieces. Which means that all in all, if I want to sum up my path over a whole bunch of these little intervals, I'm going to be looking at the sum of all of these little pieces. Namely, the sum, as t goes from some point 0 to b, of the magnitude of r prime of t. And I'm going to pull this delta t outside of my magnitude, because the delta t, that's just some scalar. It's a real valued number. I can pull it out of a magnitude. Now, as my delta t gets smaller and smaller, I'm going to take my limit as my delta t goes to 0. And by the magic of calculus, we can rewrite this as an integral. So this is exactly equivalent to the integral as t goes from 0 to b of the magnitude of r prime of t dt. And this right here is the equation that we have for arc length. So if I start at some time t0, and I travel along this path until I get to some time b, really what I'm doing is I'm summing up all of these little pieces. As these pieces get smaller and smaller, I'm summing up the pieces which are the magnitude of r prime of t.
Right. So we have this new function. It's going to take inputs that will be a time after our initial point. And it'll give us out the distance we've traveled to then. So we're going to be using that a lot later. But it's good in its own right. That we're going to want to be able to, at times, be able to calculate some arc lengths.
Yeah, so if I wanted to rewrite this as an arc length function, I can write S to represent arc length. This is my arc length. If I plug in some value t, I'm traveling from u equals 0 to some t of the magnitude of r prime of u du. Notice the subtle difference here. I'm computing just the straight up arc length, whereas this is a function. This is a function where my input is the amount of time that I've traveled and my output is the length of that arc.
Also, before we get any further, we want to revisit speed, the speed at which we travel. If we have our cool path and we're traveling along, we have the velocity vectors at any given point. We could be going really fast as we go up this hill, and really fast, and maybe slow down maybe later, slow down later, slow down later. This is all going to be determined by the parameterization we have for our original function. But we've been calculating speeds before.
We've calculated velocity before.
Velocity before. Speed is always a positive idea for velocity. So speed is going to be the magnitudes of our velocity vectors. Now, that's what these are. Here, magnitudes of velocity vectors. That's going to be popping up again and again.
So you can talk.
Okay.
You can record this, that speed is going to be equal to the magnitude of our velocity vector. And as we recall, our velocity vector is actually the derivative of the tangent vector.
So geometrically speaking, we have lots of parameterizations for different curves. There can be reasons why we would want to make these easier, more malleable maybe. There are some ways of we can treat these a little differently. One thing we can do is, while tracing out the same curve, we could instead try to figure out a way to travel this curve at 1 unit per second. Now right now my velocities are, I go real fast, then I go real slow. I might want to have the same curve, but have all my velocities be exactly 1 all of the time. So to do this, we're going to have to relate somehow our time, our speed, and normalize this idea. We have ways of normalizing vectors now. We take the vector itself, we end up dividing by its magnitude to get the vector of the same direction, but of length 1. We're going to try and apply some of our thoughts of normalizing our parameterization in order to give us the same path, but with speed 1 at all times. So let's see.